Hi, Assalamualaikum and a very good morning. So now we are still in chapter 1, which is matter, but now we're going to focus on the subtopic of 1.2, mole concept, part 2 of the video. So in this video, we're going to look into the definition of the term empirical and molecular formula, as well as we're going to determine the empirical formula and molecular formulae from the mass composition or the combustion data. For the subtopic A and B here, we have covered that in part 1 of the video, which is in the previous video. So if you haven't watched that one, please watch it now. For now, we're going to focus on the subtopic C and D, which is part 2 of the video. So without any further ado, let us start. So empirical formula and molecular formulae. So the definition of empirical formula is that it is a chemical formula that shows the simplest ratio of atoms of the element present in a compound. Meanwhile, the molecular formula is a chemical formula that shows the actual number of atoms of each element in a molecule. So the best way to understand that is to look at the table here. For example, the hydrogen peroxide will have a molecular formula of H2O2. Okay, the actual number of the actual formula is going to be H2O2, and this can be simplified to become HO because 2 and 2 here can be simplified further into 1 and 1. So HO here refers to the empirical formula. Same goes to benzene, where the molecular formula is going to have C6H6, and we can simplify that into CH. Okay, so the relationship between empirical formula to molecular formula is the empirical formula can be enclosed by a bracket N. Okay, for example, in this case, HO bracket 2 is the same as H2O2. Okay, and the N here needs to be in terms of integers. So integers means that it need to be whole number. So it can be 1, 2, or 3. It cannot be 1.33. It cannot be 2.79. Okay, so it needs to be a whole number. So to understand more about this, let us look into the example. So for empirical formula and molecular formula, we need to be able to determine the empirical formula first. So there are three situations. The first one is by using a percentage of composition of a compound. Number 2, by using the masses of a compound. And number 3, by using the combustion data or the elemental analysis data. So for the situation number 3, it is quite lengthy, but essentially all these three situations, 1, 2, and 3, will use the same technique, which is using the Marmora table. So what is Marmora table? So Marmora table are basically a table that consisting of an element, for example, element A and element B, and then we're gonna create a row of mass, number of moles, and also the simplest ratio of mole in order to determine the empirical formula. So what we're gonna have is Ma, which is mass, moles for mole, and then simplest ratio, which is Ra. So that is why the table names Marmora table. Okay, so now let us look into each of the situation one by one. So for example, number 1, which is by using percentage of composition of a compound. So a sample of hydrocarbon will contain 85.7% carbon. Okay, so carbon level as C, and 14.3% hydrogen by mass. Its molar mass is 56. So we need to determine the empirical formula and the molecular formula of the compound. So by using the percentage here is that we're going to assume the percentage to be as mass. Okay, because it's stated here. So we can assume that 85.7% to be 85.7 gram for carbon and 14.3 gram for hydrogen. Okay, and as you know that hydrocarbon contain carbon and hydrogen. So in order to determine the empirical formula, we have to use Marmora table. So we're going to create a Marmora table. So the elements that we have is carbon and hydrogen. Okay, so the mass of carbon going to be 85.7 gram, and then for hydrogen going to be 14.3. And now we need to find the number of mole. So the number of mole, we can calculate that by dividing mass dividing by molar mass. So 85.7, we're going to divide by the molar mass of carbon, which is 12. Okay, so what we're going to get is 7.141. So we're going to repeat that on hydrogen as well. So the mass of the hydrogen is 14.3 gram divided by the molar mass of the hydrogen, which is 1. So what we're going to get is 14.3. Okay, and now we're going to find the simplest ratio. In order to get the simplest ratio, we need to divide these numbers with the smallest number between these two. So in this case, 7.141 is smaller than 14.3. So you know that 7.141 going to divide it by itself, which equal to 1, and 14.3 going to be divided by the smallest number here, which is 7.141 also. So what we're going to get is roughly 2 here. So we can say that the empirical formula equal to C1H2. Okay, and usually number 1 here is ignored. So we're going to write it as CH2 only. Okay, so we're done with the empirical formula. And now we need to find the molecular formula. So we know that CH2 bracket N is equal to the molecular formula. Okay, so the molecular formula here is given the molar mass, which is 56. So you know that the CH2 bracket N is equal to the 56. So you can find the molar mass of the empirical formula first, where the carbon is equal to 12 plus 2 times 1, because we have 2 hydrogen and the molar mass of hydrogen is 1. So essentially you will get 14N is equal to 56. So N, we're going to get 4. Okay, and now we can substitute N equal to 4 into this empirical formula. Okay, so we have CH2 bracket N, where our N is 4, and hence we can get the molecular formula to be C4Hn. Okay, and this is how you find the empirical formula and the molecular formula by using percentage of composition of a compound. Now we're going to look into the next situation, which is using masses of a compound. So by using masses of a compound, it is very direct. So whatever masses that given to you, you're going to straight away use that in the Mamora table. So now let us read the question. So 18.3 gram of sample of hydrated compound. So hydrated means that it contains water. Okay, hydra means it comes from the word hydro, and hydro here refer to water. So the compound contain calcium, which is Ca, 4 gram of that, chlorine, Cl, and 7.2 gram of water only. So the water here is H2O. Okay, and then we need to calculate its empirical formula. So in order to find the empirical formula, we need to use the Mamora table. So we have the element of calcium, chlorine, and water. So for this case, because it's stated that it is hydrated, so you can straight away to use the element of water because you have the mass of water. You don't have to separate between H and O. Okay, you don't have to do that. You can straight away use H2O because it is a hydrated compound. Okay, and as mentioned, calcium will have 4 gram, chlorine gonna have 7.1 gram, and the water gonna have 7.2 gram. So as before, you need to find the number of moles, where you're gonna divide mass of the element with the molar mass of the element. So 4 gram divided by 40.1, you will get 0.0998 mole. For chlorine, 7.1 divided by 35.5, you get 0.2. And for water, you're gonna divide 7.2 divided by 18, where it equals to 2 times 1 plus the molar mass of oxygen is 16. Okay, so you're gonna be 18. Okay, so the moles that you will be getting is 0.4. Now we're gonna find the simplest ratio of mole, where we're gonna divide the number here with the smallest number between them. So the smallest number here is 0.098, right? So 0.0998 divided by itself, then we can get 1. Then we're going to repeat the same process, which is 0.2 divided by the smallest number. Okay, which is 0.098, we get 2. And then 0.4 also divide by 0.0998. So we're going to get roughly 4. And once we get the simplest ratio to be in the integer, so we can write the empirical formula to be Ca1 Cl2 dot 4H2O. Okay, for this case it is quite special because it is hydrated, so you put a dot and then number 4 at the front of the H2O here. Okay, and as usual, number 1 here is usually ignored, so we're going to write it as CaCl2 dot 4H2O because it is a hydrated compound. Okay, so now we're going to look into the next example, which is example 3, which is using combustion data or the elemental data analysis. So 1 gram of sample of organic compound A, so organic, was burned in excess oxygen. So the combustion produced 2.52 gram of carbon dioxide, 0.443 gram of water, and we need to determine the empirical formula. So you know that the empirical formula, we're going to use the Marmora table. And for this reason, we need to know the mass. Okay, and before that, we need to know what elements are present in the organic compound A. So as you know that in organic compound, as what you have learned in high school, organic compound consists of a compound with an element of carbon, hydrogen, as well as oxygen. So organic mesti ada tiga elemen tersebut. Kalau ada carbon dan hydrogen, it's gonna be known as hydrocarbon. But for all three of these, this is known as organic compound. Okay, so the combustion, so basically we need to find the mass of carbon first, the mass of hydrogen, and the mass of oxygen in order to find the empirical formula. Okay, so step number 1, calculate the mass of each atom. So carbon. So the mass of carbon, we can take that by looking into the mass of the carbon dioxide. Okay, kenapa? Because the carbon, you can see that the carbon is in the carbon dioxide. Carbon tiada dalam water. Okay, so you need to rely on the information here. So in order to find the mass of carbon in carbon dioxide, you basically need to divide, for example here, the carbon, you know that the carbon mass is equal to 12. Okay, but the total mass, the total molar mass of carbon dioxide is going to be 12 plus 2 times molar mass of oxygen. Okay, so it's going to be 44. So we need to find the mass of carbon in carbon dioxide, which is 12 divided by 44. And then we need to multiply by the mass of carbon dioxide given in the question, which is 2.52. Okay, and once we do the math, we're going to get 0.6873 gram. So you know that the mass of carbon in carbon dioxide is going to be 0.6873. So you need to repeat the same process. Now we need to find hydrogen. So for hydrogen, you can get the mass of hydrogen from water because hydrogen is in water. Okay, so the mass of hydrogen, mass of water is 0.443 gram. And in order to find the mass of hydrogen in water, you basically need to identify the mass of water, the mass of hydrogen, which is 1, divided by the total mass of water, which is 2 plus 16, we're going to get 18, times the total mass of water given in the question, which is 0.443 gram. So once you do that, okay, the mass of hydrogen here got 2, so we're going to multiply it by 2. Okay, so they're going to get 2 times 1 divided by 18. So lastly, you're going to get the mass of hydrogen to be 0.0449 gram. Okay, so carbon done, hydrogen done. Now we need to find the mass of the oxygen. So the mass of oxygen is present. Okay, oxygen itu ada dekat carbon dioxide dan oxygen itu pun ada dekat water. So how are we going to do that? So you know that the mass of carbon is given as here 0.6873 and the mass of hydrogen is 0.049 gram. So the best way to do that is we can deduct from the sample. So you know that the sample A contain carbon, hydrogen and oxygen. So the total gram here, the total mass is going to be 1 gram. So in order to find oxygen, 1 gram, we can deduct it with the mass of carbon and we can deduct it with the mass of hydrogen in order to get the mass of the oxygen. So once we find the difference, the mass of oxygen going to be 0.2635 gram. So now we already got the mass of carbon, the mass of hydrogen, and the mass of oxygen. Okay, and we can do the Mamura table. So we're going to continue that on the next slide. So for the next step, we need to use the Mamura table to determine empirical formula. So the Mamura table is going to look as here, which is carbon, hydrogen, and oxygen. And we have the mass, moles, and the ratio. So the mass of carbon, as in the previous slide, is equal to 0.6873. Hydrogen will equal to 0.0492. And for oxygen is 0.2635. Okay, so if you add up this one, is equal to 1 gram. So the mass of carbon, the mass of hydrogen, and the mass of oxygen is equal to 1 gram, as mentioned in the question here. Okay, now in order to find the number of mole, the same as step as before, which is mass divided by molar mass. So 0.6873 divided by the molar mass of carbon, which is 12, you're going to get 0.0573. For hydrogen, you're going to get 0.0492 divided by 1, where you're going to get 0.0492. And for oxygen, the mass here is 0.2635 divided by the molar mass of oxygen, which is 16. So you're going to get 0.0165. So among all these three values, this one is the smallest. So we're going to divide 0.0573 with the smallest value in order to find the simplest ratio. Okay, so once we do the division, we get 3.5. 0.0492 divided by 0.065, we're going to get 3 for hydrogen. And for oxygen, 0.0165 divided by 0.0165, we're going to get 1. Okay, so you can say that the empirical formula is going to be C 3.5, hydrogen 3, and oxygen 1. Okay, however, as I mentioned that the ratio needs to be in integers. It needs to be a whole number. Dia mesti 1, 2, 3, 4. Dia tak boleh ada perpuluhan. It cannot be in decimal places. So, in order to remove the decimal places, everything here needs to multiply by 2. Here multiply by 2 as well. And here also multiply by 2. So, 3.5 times 2, you're going to get 7. Hydrogen here, we're going to get 3 times 2, which is 6, and 1 times 2 equal to 2 oxygen. So at last, the empirical formula that we are getting is C7H6O2, and this is the correct one, which is C7H6O2. Okay, so I think that's all for today's video. See you again some other time. Bye!